Large electrical grids cover wide geographic areas. They include many generators, transmission lines, substations, and distribution systems. These components are connected so that power can flow from where it is produced to where it is consumed. Multiple local systems become part of a single coordinated region. The scale of such regions can be a single state, several states, or an entire country. In some cases, they cross international borders. The defining feature is an organized network of equipment and operations that work together. At the core of a regional grid is the idea of interconnection. An interconnection is a set of transmission lines and power plants that operate together at a common alternating current frequency. Operating at a common frequency allows power to move freely across the network. Frequency is a simple number that describes how often the current alternates each second. Keeping that number close to its target is one of the primary tasks of a regional grid. When generation and consumption are nearly balanced, the frequency stays near its scheduled value. When they are not balanced, frequency moves away from the scheduled value. Managing that balance requires coordination among many entities. Within a regional grid, control areas are established. Each control area is responsible for balancing generation and load inside its boundaries. Control areas are often called balancing authorities. They monitor generation, load, and the power exchanged with neighboring areas. The power exchanged occurs over tie lines. Tie lines are transmission lines that connect control areas. Operators set schedules for how much power will flow across these tie lines over defined periods. These schedules reflect planned exchanges for energy, seasonal needs, or market transactions. Maintaining flow close to the scheduled amount is part of normal operations. Operators use several layers of control to keep the system stable. The fastest, automatic, layer involves equipment on generators. Governors adjust the output of turbines in response to small frequency changes. This action happens in seconds. A second automatic layer is often called Automatic Generation Control, or AGC. AGC adjusts the output of selected generators to correct remaining frequency deviations and to maintain tie line flows near their schedules. These automatic systems act continuously. They make small corrections that keep the network operating smoothly. Beyond automatic controls, there are procedures and agreements that define how regions coordinate. Regional reliability organizations set technical standards and coordinate planning studies. Transmission operators and balancing authorities share data on expected demand and generation availability. They run day-ahead and hour-ahead schedules to plan how generation will be dispatched. Markets can be part of this planning. Market mechanisms enable generators to offer capacity and energy. Market clearing determines which resources will operate. When market outcomes are combined with physical constraints, operators derive schedules that are feasible on the network. Physical constraints shape how the system operates. Transmission lines have limits on how much power they can carry. Lines heat up as current flows and require clearance limits. Substations and transformers have ratings that must not be exceeded. When planned flows approach limits, operators may redispatch generation or reconfigure switching to relieve constraints. Contingency planning is another important aspect. Operators identify critical equipment that, if lost, would create overloads or unacceptable conditions. They plan corrective actions in advance. These actions can include redispatching generation, reducing imports, or shedding load in extreme cases. Contingency planning is based on studies that simulate the loss of single or multiple elements and ensure the system can remain stable. Redundancy and diversity contribute to regional reliability. Redundancy means there are multiple paths for power to flow. If one path is unavailable, power can be rerouted through another. Diversity refers to the mix of resource types across the region. A mix of thermal plants, hydroelectric plants, wind, solar, and storage provides different response characteristics. Some resources can ramp quickly, others provide steady output. Sharing these resources across a region reduces the need for each local area to carry all of its own reserves. Reserve sharing is often formalized in agreements. These reserves are held to cover sudden changes in demand or unexpected losses in generation. Coordination across time zones and weather patterns also plays a role. Day-night cycles, seasonal variations, and weather fronts create predictable shifts in demand and generation. A region spanning a large area may experience different conditions at the same time. This spatial diversity smooths out some variability. Operators use forecasts to plan for expected changes. Forecasts for load and for renewable generation feed into scheduling and reserve decisions. When actual conditions differ from forecasts, the automatic and human control processes respond to restore balance. Communication systems and monitoring are essential for coordination. Sensors across the grid report voltages, currents, and frequency. Phasor measurement units provide precise, time-synchronized data that reveal how the grid behaves in near real time. Control centers collect and display this data. Operators analyze trends and make adjustments. State estimation algorithms process measurements to produce a coherent picture of the system. This picture informs dispatch decisions and contingency responses. Interregional coordination occurs when separate regional grids exchange power. These exchanges can help manage surplus generation, share reserves, and optimize resource use. Tie line schedules between regions are negotiated and monitored. When an unexpected event affects one region, neighboring regions can provide support through predefined arrangements. Such support can include emergency energy, reserve sharing, or temporary reconfiguration of flows. Interregional coordination requires compatible technical standards and clear communication protocols. The result of these layers of equipment, procedures, and agreements is a system that behaves as a single coordinated entity across a large area. Local actions can have system-wide effects. Automatic and manual controls act together to correct imbalances. Planning and operation take place on multiple timescales, from seconds to months. Through interconnection, regions achieve benefits in reliability and efficiency. They pool resources, share risks, and manage variability. The grid's structure and governance enable many independent entities to operate as a unified system. The overall behavior emerges from the interaction of physical, infrastructure, control systems, and institutional arrangements. Power generation facilities supply electricity to the grid by producing alternating current at a controlled frequency and voltage. Each facility converts some form of energy into electrical energy. Common conversions include mechanical rotation in turbines, chemical reaction in fuel cells, and photovoltaic conversion in solar panels. The electrical outputs from these sources enter a shared network of conductors and equipment. That network is the regional grid. Supply must match demand continuously. The mechanisms that achieve that balance operate both locally and across large areas. Thermal power plants, such as those driven by steam turbines, burn fuel to produce heat. The heat produces steam that turns a turbine. The turbine is coupled to a synchronous generator. The generator produces alternating current. Hydroelectric plants use flowing water to turn turbines directly. Wind plants use wind-driven blades to turn generators. Solar plants produce direct current, which is converted to alternating current by inverters. Each generator or inverter is connected to the grid through transformer equipment. Transformers step electrical voltage up for efficient transmission and down for local distribution. Several generation sources operate in parallel on the same grid. Parallel operation means that multiple generators are electrically connected to the same network. They must share the same frequency. They must be synchronized in phase and voltage before connection. Synchronization ensures that alternating waveforms align closely enough to avoid current surges when a connection is made. Control systems verify frequency, phase angle, and voltage. Switchgear then closes to place a generator in parallel with the grid. Once connected, a generator contributes a portion of the total power flow. Power sharing among generators relies on a mix of automatic and manual control. Governors on turbines respond to changes in system frequency. When demand increases suddenly, frequency tends to fall. A turbine governor senses the change. It increases mechanical input to the turbine. Generator output rises in response. The opposite occurs when demand falls. Automatic governor action provides the first and fastest level of response. A second layer of control adjusts generator set points over a longer time frame. This is often called centralized dispatch or automatic generation control. Centralized dispatch monitors system frequency and scheduled flows and issues. Adjustments to maintain a steady balance between generation and load. These adjustments are typically made in small steps, distributed among generators according to their capabilities and operational constraints. Generators also manage voltage and reactive power. Voltage at a node in the grid is influenced by real power flow, reactive power flow, and the electrical characteristics of lines and transformers. Synchronous. Generators adjust their field excitation to absorb or supply reactive power. Diesel and gas turbines have excitation systems that respond to commands from voltage regulators. Inverter-based sources, like solar arrays and some battery systems, can modulate reactive power through control algorithms. Voltage regulation helps maintain acceptable voltage levels for end users and for equipment protection. Continuity of supply is supported by a portfolio of generation types. Base load units run continuously to provide a steady portion of demand. Mid-merit and peaking units operate to follow daily and short-term demand variations. Hydroelectric plants can serve either base load or peaking roles, depending on available water and operational priorities. Fast response units, such as simple cycle gas turbines and some battery systems, provide quick changes in output when required. The mix of units is planned to ensure that at any moment the system has enough resources that can increase output and decrease output as needed. Reserve capacity is an important part of operations. Spinning reserve consists of generation capacity that is online and synchronized, but operating below its maximum output. It can increase output almost immediately when needed. Non-spinning reserve refers to capacity that can be brought online within a defined time, such as through starting additional turbines or activating demand-side resources. Reserves are scheduled based on expected demand, historical variability, and uncertainty in supply. When a generator trips offline or when a rapid change in consumption occurs, reserve capacity is dispatched to restore balance. Control centers coordinate these functions across regions. Operators monitor system frequency, voltages, line flows, and generation outputs. They use tools that display real-time and forecasted conditions. Dispatchers issue commands to change generator outputs. In many systems, an automatic generation control system provides continuous small adjustments. These adjustments correct for minor deviations from scheduled flows and frequency. The system follows predefined agreements and operational limits. Coordination across multiple control areas allows larger balances to be maintained more efficiently. Interconnected grids can share resources and reserves, spreading the responsibility for balancing. Inverter-based resources introduce different dynamics. Solar and wind farms connect to the grid through power electronics. These inverters convert direct current or variable frequency, alternating current into the grid frequency. They do not always provide the same inertia effects as synchronous generators. Inertia is the property of rotating masses that slows the rate of change in frequency when system conditions change. To manage this, system operators rely on fast-acting reserves, synthetic inertia provided by some modern inverters, and energy storage systems. Batteries can inject or absorb power quickly. They can provide frequency support and ramping services. The integration of these resources requires planning and control strategies to preserve stability. Legal and market mechanisms influence which generation units run at any time. Markets determine economic dispatch based on bids, prices, and contractual arrangements. System operators factor in reliability constraints and reserve requirements when committing units. Commitment schedules set which generators will operate over coming hours and days. Those schedules are adjusted as conditions change. Maintenance planning also plays a role. Plants are taken offline for scheduled maintenance in ways that keep sufficient capacity available. Emergency plans exist for unscheduled outages. Physical connections among generators and loads shape power flows. Transmission lines carry bulk power over long distances. Substations route power through transformers and switches. Power flows follow the electrical network according to physical laws. Operators use power flow analysis to predict how changes in generation or load will affect line loading and voltages. They may redispatch generators or reconfigure network elements to avoid overloads. Protection systems isolate faults to prevent equipment damage and to keep the rest of the grid functioning. Continuous operation depends on monitoring and feedback. Sensors measure frequency, voltage, current, and equipment status. Control systems process this data. Automatic responses occur on timescales from milliseconds to minutes. Manual interventions occur when needed. The layered structure of control, from local governors and inverters to centralized dispatch, creates a system capable of maintaining a continuous electrical supply. Multiple generation sources operating in parallel provide redundancy and flexibility. This arrangement allows the grid to accommodate routine changes and unexpected events while delivering electricity across large regions. High-voltage transmission lines move electrical energy from places where it is generated to places where it is used. The primary goal of a transmission system is to transfer large amounts of power across long distances with minimal loss. Voltage, current, and resistance are the basic electrical variables that determine how efficiently this transfer occurs. Raising voltage reduces current for a given power level. Lower current reduces heat losses in conductors. That relationship underpins the widespread use of high voltages on long transmission routes. Transmission lines typically operate at tens to hundreds of kilovolts. Those voltages are not arbitrary. They are chosen to balance technical performance, cost, and safety. Higher voltage allows power to flow with smaller current. Smaller current means less energy lost as heat in the conductor. At the same time, higher voltages require larger insulators, taller towers, and greater clearances. Engineers select voltage levels that match the distance and capacity required for a particular corridor. Transformers are central to making high-voltage transmission practical. A transformer steps up voltage at the generation site before the power travels long distances. At the delivery end, another transformer steps the voltage down to levels used by distribution networks and consumers. The step-up and step-down process uses magnetic coupling between coils. It changes the voltage without converting the electrical energy into another form. By stepping voltage up before transmission and stepping it down near load centers, transformers reduce losses while permitting safe, usable voltages near consumers. Conductor choice also affects efficiency. Most overhead lines use conductors that combine aluminum with a steel core. Aluminum provides good conductivity per unit weight. The steel core gives tensile strength to support long spans between towers. Variations in conductor design address different priorities. Some conductors prioritize low resistance. Others prioritize mechanical durability and resistance to weather. In densely populated or constrained corridors, bundled conductors are common. Bundling places 2 or more conductors per phase. That arrangement reduces the electric field strength around each conductor and lowers losses due to corona discharge. It also improves the line's capacity to carry current. Line losses are primarily resistive, often described by the formula for I squared R losses. They increase with the square of current. That makes current reduction a priority for long-distance transfer. Other loss mechanisms include corona discharge, dielectric losses in insulators, and radiation at very high frequencies. Corona becomes more significant when conductors carry high voltage and when surface irregularities or humidity are present. To mitigate corona and audible noise, engineers select conductor size, spacing, and surface finish with care. Electrical flow on transmission lines is alternating current in most regional grids. Alternating current allows transformers to change voltage levels with relative ease. It also supports synchronous operation across wide areas, which simplifies the sharing of generation among multiple sources. AC transmission, however, introduces reactive power. Reactive power does not deliver net energy, but affects voltage levels and the apparent power flowing on the line. Managing reactive power is part of maintaining efficient operation. Devices such as capacitors, reactors, and synchronous condensers are deployed at substations and along corridors to control voltage and reactive flows. High voltage direct current transmission is an alternative used in particular circumstances. HVDC is efficient for very long distances, for submarine cables, and for linking asynchronous networks. Unlike AC, DC does not require reactive power management and avoids certain stability issues. HVDC terminals are more complex because they convert between AC and DC. The conversion equipment adds cost at each terminal. For corridors that span very long distances or cross bodies of water, the trade-offs often favor HVDC. Physical support structures form the backbone of transmission routes. Towers and poles maintain the necessary clearance between conductors, ground, and obstacles. Tower types range from simple steel lattice structures to tubular steel poles. Design choices respond to terrain, climate, and right-of-way constraints. Towers also provide insulator mounting points. Insulators isolate the conductors from the tower structure while bearing mechanical loads. They are made from materials such as porcelain, glass, or composite polymers. Their design ensures that the electrical path does not cross into grounded structures. Line geometry affects performance. Span length, conductor height, and sag are interrelated. Sag is the downward curve that forms between support points under the conductor's weight and thermal expansion. Sag must be controlled to preserve clearances and to limit mechanical stress. Higher temperatures increase sag as conductors expand. Wind and ice loads add additional mechanical demands. Engineering standards and safety margins guide the allowable sag for a given route and conductor type. Routing decisions balance technical, environmental, and economic factors. Transmission corridors are planned to minimize overall cost while connecting generation and load centers effectively. Routes seek to avoid difficult terrain when possible, but may cross such areas when necessary. Redundancy is often built into routing through parallel lines or looped configurations. This approach increases reliability by providing alternate paths for power if a single line is taken out of service. System planning frequently applies criteria that require the network to withstand the loss of a single element without widespread interruption. Substations provide critical interfaces along transmission routes. They contain transformers, circuit breakers, switches, and protective equipment. Circuit breakers interrupt current to isolate faults. Protective relays detect abnormal conditions and trigger breakers. Switchyards allow operators to reconfigure the network for maintenance or to respond to changing load patterns. Substations also host monitoring devices that measure voltage, current, frequency, and power flow. These measurements feed control systems that coordinate operation across the grid. Maintenance and monitoring support stable long-term operation. Inspection regimes use ground patrols, aerial surveys, and increasingly, drones and sensors. Thermal cameras can detect overheated connections. Sag monitors and vibration dampers help preserve mechanical integrity. Vegetation management underlines practical reliability. Trees and other vegetation that encroach on corridors can create fault conditions, so rights-of-way are managed to maintain clearance. Finally, operational coordination across regions contributes to efficient use of transmission assets. System operators monitor flows and dispatch generation with an eye toward minimizing losses and maintaining acceptable voltages. Power flow studies and contingency analyses guide operational decisions. Scheduling and market mechanisms influence which generators supply energy at what times. Those economic signals interact with the physical constraints of the transmission system. Throughout these elements, a consistent principle governs design and operation. Efficient transfer of energy over distance relies on minimizing current, managing voltage, and maintaining the physical infrastructure that supports conductors. Each technical choice reflects trade-offs among efficiency, cost, and practical constraints. The resulting network combines electrical theory with civil and mechanical engineering to move bulk electricity across regions. Substations are the sites where electrical voltage is altered and prepared for movement between large transmission lines and local distribution networks. They serve as junctions. They change voltage levels. They also provide switching, protection, and measurement functions. These tasks allow electricity to move efficiently and reliably from generators to consumers over varying distances. Two basic types of substations are commonly described. Transmission substations connect and manage high-voltage lines that carry power across long distances. Distribution substations reduce voltage to levels suitable for neighborhoods and businesses. Some facilities serve both roles in successive stages. In each case, transformers are the main devices used to change voltage levels. A transformer changes voltage by means of electromagnetic induction. It has primary and secondary windings wrapped around a magnetic core. The ratio of turns between the windings determines whether voltage is stepped up or stepped down. A generator output is often stepped up to very high voltage for transmission. This reduces current and lowers losses in long lines. Near load centers, substations step voltage down to lower levels to feed regional and local networks. Voltage regulation is a continuous activity within substations. Loads vary across hours, days, and seasons. These variations cause voltage at different points in the grid to change. Substations use several mechanisms to maintain voltage within required limits. On-load tap changes alter transformer winding ratios, while the transformer remains energized. This allows small, discrete adjustments to the output voltage as load changes. Off-circuit tap changes are used when service can be interrupted for maintenance. Additional devices such as automatic voltage regulators provide more refined control when needed. Reactive power, which is distinct from the real power consumed by loads, affects voltage levels along the network. Capacitor banks supply reactive power locally. Reactors absorb reactive power when necessary. Some substations include synchronous condensers or static compensators for dynamic control. These devices help stabilize voltage during changes in load or line conditions. Managing reactive power reduces voltage drop over distance and improves the ability of the network to deliver usable power. Switching equipment is essential in a substation. Circuit breakers can interrupt current flows quickly. Disconnect switches provide visible isolation for maintenance. Bus bars collect and distribute power inside a substation. Different bus arrangements exist, such as single bus, double bus, and breaker-and-a-half configurations. These arrangements influence redundancy and ease of maintenance. Redundancy allows parts of a substation to be taken out of service without interrupting supply to connected areas. Switching also supports the reconfiguration of networks to respond to faults or planned outages. Protection systems detect abnormal conditions and act to isolate faults. Protective relays monitor currents, voltages, and other parameters. When a relay detects a fault, it sends a trip signal to circuit breakers. This isolates the affected equipment or line. The response prevents equipment damage and limits the area affected by a fault. Instrument transformers, such as current transformers and potential transformers, provides scaled-down signals to relays and meters. These measurement devices enable accurate monitoring and protection without exposing sensitive equipment directly to the high voltages present on the primary side. Grounding, or earthing, is another fundamental element. Proper grounding provides a reference potential for the electrical system. It reduces the risk of uncontrolled voltages during faults. Grounding systems connect equipment frames, neutral points, and ground grids to dissipate fault currents safely into the earth. Substation grounding design considers soil resistivity, fault, current magnitude, and operator safety protocols. Grounding also supports coordinated protection schemes by providing predictable paths for fault currents. Control and monitoring are centralized in control rooms or distributed through remote units. Supervisory control and data acquisition systems collect status information, measurements, and alarms. Remote terminal units and protective relays communicate with system operators and with automated control systems. Communications use a range of media, including fiber optic cables, microwave links, and in some cases, power line carrier systems. This exchange of information allows operators to observe voltage levels, switchgear positions, and equipment health. It also enables automatic responses to certain conditions, such as reclosing breakers after transient faults. Cooling and insulation are practical concerns for equipment that handles high power. Transformers often use mineral oil or other insulating fluids. Oil provides both electrical insulation and heat transfer. Radiators, cooling fans, and pumps maintain operating temperatures within design limits. Gas-insulated switchgear encloses live parts in an insulating gas to reduce the footprint and limit exposure to the environment. Insulators made of ceramic or composite materials support conductors and prevent unintended current flow to grounded structures. Maintenance and testing are regular activities. Breaker timing tests, oil sampling and analysis, thermal imaging and relay testing reveal degradation before failure occurs. Scheduled maintenance minimizes the risk of unexpected outages. Components such as transformer bushings and insulators are inspected for mechanical and electrical integrity. Maintenance uses established procedures that include isolation, grounding, and verification steps to ensure safe work conditions for personnel. Losses occur in transformers and switchgear. Core losses and copper losses reduce the net power available for delivery. Substations balance the efficiency of equipment with the need for flexibility, protection, and control. Placement of substation equipment, transformer sizing, and capacitor installation are planned to reduce losses across typical operating conditions. Planning also accounts for future load growth and the need to reconfigure connections as demand changes. Interconnections between regions pass through substations designed to manage transfers. Phase-shifting transformers can control power flows between asynchronous areas. High-voltage direct current converter stations also connect distant systems and require substation interfaces. These interconnections allow power to be shared across wide areas, which helps balance generation and demand. Operators manage such transfers according to agreed protocols and system constraints. In operation, a substation performs a sequence of tasks repeatedly. It receives power at one voltage. It measures currents and voltages. It adjusts voltage levels as needed. It provides switching and protective actions when necessary. It communicates status to control centers. It facilitates distribution to local feeders. These functions together make substations critical nodes in the larger electrical grid. Descriptions of substations emphasize their technical roles rather than aesthetic qualities. The equipment and systems present are selected and arranged to meet electrical, mechanical, and operational requirements. The design balances cost, reliability, and adaptability. Over time, upgrades and replacements are carried out to reflect changes in demand, technology, and regulatory standards. Substations continue to serve as essential elements in the process of preparing electricity for use at regional and local scales. Electrical systems operate by keeping supply and demand in balance at every moment. When generation and consumption are equal, the system frequency remains near its nominal value. When they differ, frequency moves away from nominal. Frequency is the primary indicator that the system is balanced. Small deviations in frequency prompt a sequence of automatic and controlled adjustments across generation and demand. The first layer of adjustment is an automatic local response built into many generators. Steam, hydro, and gas turbines have governors that sense small changes in rotational speed. When speed drops slightly, the governor opens valves to add fuel or water. When speed increases, the governor reduces input. These mechanical actions act within seconds. They arrest the initial change in frequency. They are often called primary or governor response. This response is distributed across many machines and takes place without centralized commands. Following the immediate governor actions, secondary control works on a slightly slower time frame. Control centers monitor system frequency and the output of individual generators. Automatic generation control, or AGC, issues set point changes to adjust generator outputs. AGC signals are sent over communication links to selected units. The goal is to restore frequency to its scheduled value and to correct area control error, a measure of imbalance in a defined region. Secondary control operates over minutes. It adjusts generation so that primary responses are no longer relied upon to hold frequency. Tertiary control manages longer duration adjustments and reserve allocation. Market dispatch and operator decisions reassign generators, bring additional units online, or start fast start resources. Tertiary actions occur when sustained imbalances need correction or when reserves need replenishing after a contingency. These actions can take tens of minutes to hours, depending on the resources involved and their startup times. Reserves are a critical element of balancing. Spinning reserve consists of generating capacity already synchronized to the grid and ready to increase output quickly. It can respond within seconds to minutes. Non-spinning or supplemental reserve includes units that can start and supply power after a brief delay, or demand-side resources that can reduce consumption on command. Maintaining adequate reserves allows the system to cope with sudden losses of generation or unexpected increases in load. Inertia provided by large rotating machines influences how rapidly frequency changes. Inertia slows the rate of change of frequency immediately after a disturbance. Traditional synchronous generators naturally provide inertia through their rotating mass. As more inverter-connected resources, such as solar and wind generators, are added to the system, conventional inertia may decrease. To address this, some inverter-based resources are configured to provide fast frequency response or synthetic inertia. These controls can inject or absorb power very quickly, based on measurements to help limit frequency deviation until slower controls act. Forecasting plays a continual role in balancing. Load forecasts are produced for timeframes from seconds to days ahead. Weather forecasts, historical consumption patterns, and scheduled generator outages inform these predictions. Forecasts help operators plan unit commitment and dispatch. When actual conditions differ from forecasts, real-time adjustments are made. These adjustments may involve changing generator outputs, activating reserve resources, or modifying imports and exports across interconnections. Transmission interconnections allow regions to share resources. Balancing authorities coordinate across tie lines to move power from areas with surplus to areas with deficit. Tie line flows are monitored and controlled. Scheduled exchanges are part of daily operations. When unexpected events occur, neighboring areas assist by providing reserves. The contractual and operational arrangements that govern these exchanges help maintain regional stability and allocate the costs of balancing. Voltage control and frequency control are related but distinct responsibilities. Frequency reflects the balance of real power measured in watts. Voltage depends primarily on reactive power measured in volt-amperes reactive. Devices such as tap-changing transformers, capacitor banks, reactors, and synchronous condensers manage voltage levels. Inverters can also provide reactive power support. Maintaining voltage within limits ensures equipment operates properly and that power transfers across transmission lines remain efficient. Monitoring systems provide the data needed for balancing. Supervisory control and data acquisition systems, SCADA, report generator outputs, power flows, and breaker statuses at regular intervals. Phasor measurement units, or PMUs, provide high-resolution data on voltage and current phases and system frequency. This wide-area visibility supports faster detection of imbalances and more precise control actions. Control centers process incoming data and translate it into dispatch commands or automatic controls. Demand-side measures have become more prominent in balancing. Large consumers can reduce or shift their usage in response to signals from system operators or market prices. These demand response programs can act as an alternative to increasing generation. Aggregated distributed resources, such as batteries and electric vehicle chargers, can be called upon to absorb or supply power. Their responses can be rapid and can complement traditional generation. Market mechanisms influence how balancing resources are scheduled. Energy markets, ancillary service markets, and reserve markets provide financial signals. Market participants submit bids for supplying energy or reserve services. Economic dispatch algorithms select resources to meet demand at lowest cost while satisfying reliability constraints. Market clearing processes and real-time settlement ensure that resources are compensated and that procurement is transparent. Operational procedures define priorities and responses for contingencies. For example, loss of a large generator triggers predefined steps. Primary responses stabilize frequency. Secondary controls restore frequency. Reserve activation compensates for the lost capacity. If reserves are insufficient, controlled load shedding may be employed as a last resort following established protocols. These procedures are codified and practiced. They guide operator actions during abnormal conditions. Coordination among multiple control layers is essential. Local automatic responses act first. Centralized control systems issue set points and dispatch signals. Market operations schedule resources. Physical equipment implements changes. Communication systems carry measurements and commands. The sequence is continuous. Each layer supports the others. The combination of automatic and manual, local and centralized, immediate and scheduled actions keeps the system balanced. Over time, planning adjusts to evolving resources and demand patterns. Capacity planning considers expected load growth and the role of variable generation. Operational practices adapt to incorporate new technologies and new types of services. Standards and rules evolve to define responsibilities for frequency control, reserve provision, and system performance. These changes are implemented through technical upgrades, regulatory actions, and revised operating procedures. In sum, balancing supply and demand is a multi-layered process. It begins with local, automatic responses. It continues with centralized controls and market-based scheduling. It uses reserves, forecasting, and interconnection support. It relies on monitoring, communication, and predefined procedures. Each element acts at its own pace. Together, they maintain the continuous equilibrium required for reliable power delivery. Control centers gather measurements and signals from across the power system. These facilities receive data from generation plants, substations, and transmission lines. The purpose of this data is to show current system conditions. The data includes electrical values, equipment status, and alarms. The collection of this information supports continuous assessment and timely action. A primary tool for data collection is the Supervisory Control and Data Acquisition System, commonly called SCADA. Remote terminal units at substations and plants measure voltage, current, breaker position, and other local values. These measurements are sent to the control center over dedicated communication links. SCADA provides periodic snapshots of many points on the network. The snapshots arrive with seconds to minutes of latency, depending on the configuration. Complementing SCADA, time-synchronized phasor measurement units provide high-resolution data. These devices measure voltage and current phasors with precise timestamps. The timestamps allow comparison of measurements from different locations as if they were taken at the same instant. This makes it possible to observe rapid changes in phase angle and power flow. Phasor data arrives at higher rates and with finer timing than traditional SCADA. It is useful for observing dynamic conditions that unfold within fractions of a second to several seconds. Control centers rely on a mix of observed and inferred information. State estimation is a mathematical process that creates a consistent picture of the network from imperfect data. The estimator reconciles measurements, telemetry, and known equipment models. It produces the best estimate of voltages and flows at points that lack direct measurement. State estimation runs continuously. It provides the baseline for many operational decisions. Visualization systems present the processed information to operators. Large displays and operator workstations show system maps, trends, and alerts. Trends show frequency, voltage, and power flow over time. Alarms mark limits or abnormal readings. The visual tools are designed to make it possible to notice deviations from expected conditions. The displays also show pre-calculated studies, such as contingency analyses and thermal limits. Contingency analysis simulates possible equipment failures or sudden changes in generation or load. The control center runs these studies frequently. The output identifies critical limits and potential overloads. Contingency analysis helps prioritize preventive actions. It also informs operators about corrective actions that are likely to work if a contingency occurs. Frequency is a key indicator of system balance. A sustained deviation in frequency indicates a mismatch between generation and load. Primary frequency response comes from automatic actions by generator governors and some demand-side devices. These responses act in seconds. Secondary control, often called automatic generation control, adjusts generator set points to restore scheduled interchanges and to correct area control error. This adjustment typically operates on a timescale of minutes. Tertiary control addresses longer-term rebalancing and economic dispatch. It operates on a timescale of tens of minutes to hours. Voltage control is managed separately from active power balance. Voltage depends on reactive power. Control centers monitor voltages at critical buses. They manage reactive power through generator excitation, tap changes on transformers, capacitor banks, and reactive compensators. Actions to control voltage may be automatic on local equipment or coordinated from the control center. Voltage control studies help maintain acceptable voltage profiles under varying conditions. Reserve management is central to reliable operation. Reserves are additional capacity held available to respond to disturbances or forecast errors. Different reserve categories correspond to different response times and activation methods. Spinning reserves are online and can ramp quickly. Non-spinning reserves can be started within a set time. Control centers track available reserves and commit additional resources when reserves fall below target levels. Reserve activation can be automated or manual, depending on rules and market structures. Alarms and event logging document deviations and control actions. Logs record the time and content of alarms, operator actions, and automatic controls. After an event, logs support analysis and corrective planning. The analysis identifies causes, assesses actions taken, and evaluates potential improvements to procedure or equipment. This cycle of operation, logging, and analysis contributes to incremental improvement in situational awareness and response. Communications networks link measurement devices, protection systems, and control centers. These networks are engineered for redundancy and latency requirements. Data integrity and timing are important for actionable information. Control centers apply filtering and validation to incoming data. Bad or missing data is handled through fallback procedures and estimates. When communication paths fail, alternative measures are used to maintain basic monitoring and control capability. Protection systems at local substations operate independently of control center actions. Protective relays detect faults and isolate equipment to protect assets and reduce the area affected. The control center receives status updates about protections and the resulting switching. Operators use that information to coordinate restoration and to evaluate system stability. Protection operates in milliseconds. Control center tools operate on slower timescales, but provide the broader coordination needed for system recovery. Automation supports routine and rapid responses. Automated switching schemes and remedial action schemes act when predefined conditions occur. These schemes are designed and tested before being relied upon. They can reduce the need for manual intervention in some scenarios. Operators still supervise automated actions and can override as needed. The balance between automation and human oversight varies across regions and utilities. Coordination among neighboring control areas is part of real-time management. Scheduled interchanges and unscheduled flows are monitored and adjusted. Area control error quantifies the difference between scheduled and actual exchanges, including frequency bias. Communication protocols and operational agreements define responsibilities. Coordination allows the wider system to share resources and respond collectively to disturbances. Operational decision-making combines automated calculations and human judgment. The energy management system provides studies, recommendations, and controls. Trained operators follow procedures and checklists when unusual conditions arise. Decisions may include dispatch changes, switching operations, or requests for emergency assistance. Each action is recorded and monitored for its effect on the system. Longer-term and slower processes feed into real-time operations. Day-ahead and hour-ahead schedules, maintenance plans, and market outcomes set the starting point for control room activity. Forecasts for load and generation provide expectations against which real-time measurements are compared. Adjustments are made as actual conditions deviate from forecasts. Taken together, these layers of sensing, analysis, automation, and coordination form a continuous monitoring and control framework. The framework operates across a range of timescales and spatial scales. It provides the means to observe system conditions and to apply appropriate responses as conditions change. Protection systems form an essential layer in the electrical grid. They detect faults, isolate the affected equipment, and allow the remainder of the system to continue operating. These systems combine sensors, relays, circuit breakers, and control communications. Each element performs a specific role in locating a problem and removing it from service. A fault may be a short circuit on a transmission line, an internal failure in a transformer, or an unintended connection to ground. When a fault occurs, electrical currents and voltages change rapidly. Protection devices monitor these changes. They compare measured values against thresholds and predefined rules. When measurements cross those thresholds, protection relays issue commands to circuit breakers. Relays are decision-making devices. Some relays respond to the magnitude of current. These are often called overcurrent relays. Others detect differences between currents entering and leaving a device. These are known as differential relays. A differential relay can identify an internal fault in equipment, such as a transformer or a generator, by comparing signals from two or more locations. Distance relays operate on a related principle. They estimate the electrical distance to a fault using the relationship between voltage and current. Distance protection helps to isolate faults on long transmission lines. Circuit breakers carry out the physical action of opening and interrupting current flow. They are rated for high voltages and are designed to extinguish the electrical arc that forms when a circuit is opened under load. Breakers open when instructed by relays. They can also reclose automatically in some applications, which is useful for clearing temporary faults. Reclosing is typically performed by automatic reclosers at distribution and transmission levels. When a temporary fault, such as a tree branch contacting a line, clears quickly, reclosing restores service with minimal interruption. If the fault persists, reclosing is followed by an open state and a lockout condition, signaling the need for manual intervention or different automated steps. Coordination among protective devices is a key concept. Protection coordination ensures that the device closest to the fault operates first. This minimizes the portion of the system that is disconnected. Time-current coordination is one common approach. Devices are set with different operating times based on the current magnitude. A device seeing a very high current will operate faster, while devices farther upstream wait a short time to allow the closer device to act. This layered approach provides both speed and selectivity. Backup protection supplements primary protection. If a primary relay or breaker fails to clear a fault, backup devices operate after a short delay. Backup schemes can be local, using neighboring relays and breakers, or remote, using communications between substations. Pilot protection schemes use dedicated communications channels to compare signals between two ends of a protected line. These schemes can operate faster and with greater precision than local-only approaches. Fiber optic links, microwave links, and power line carrier signals have been used for pilot protection. Modern protection systems increasingly use synchronized measurement technology. Phasor measurement units, or PMUs, sample voltage and current waveforms at high speed and tag those samples with precise timestamps. When data from multiple PMUs are combined, operators and automated systems gain a wide area view of system conditions. This view supports special protection schemes that act on a regional basis to isolate faults and limit their effect. These schemes can trigger controlled actions such as opening specific breakers or shedding predefined loads to preserve overall system integrity. Sectionalizing devices and protective relays work together to isolate faults to as small an area as possible. On distribution networks, protective devices include fuses, reclosers, and sectionalizers. Fuses are simple devices that open when current exceeds a threshold for a given time. Reclosers can open and close automatically. Sectionalizers count operations and open only after a nearby recloser has operated a set number of times, ensuring coordination and limiting unnecessary outages. On transmission systems, breaker and a half or ring bus arrangements can limit the number of circuits interrupted when there is a fault on a bus or a line. Transformer and generator protection use specialized schemes. Transformer differential protection measures current on both sides of a transformer. Any imbalance beyond an allowed tolerance triggers an operation. Generator protection includes overcurrent, differential, loss of field, and out-of-step protection. Out-of-step protection senses when a generator is no longer synchronized with the rest of the system and isolates it to prevent further disturbance. Breaker failure protection is another layer. If a breaker fails to interrupt a fault when instructed, associated protection detects the failure and initiates alternative actions. These actions may include tripping adjacent breakers or opening breakers at both ends of a line. The goal is to remove the fault from the network, even if a single breaker does not operate as intended. Ground fault protection addresses faults to earth. These faults can produce unbalanced currents that require distinct detection methods. Neutral grounding schemes and ground fault relays work together to detect and clear these specific types of faults, while limiting equipment stress and transient overvoltages. Operational control systems support protection. Supervisory control and data acquisition systems provide command, monitoring, and historical records. Energy management systems assist operators in evaluating protection actions and in authorizing special control measures. During complex events, automated protection acts faster than manual intervention. However, control room tools provide situational awareness and allow operators to implement coordinated recovery procedures after isolation. Distributed generation introduces additional considerations. When local generation is connected to the distribution network, protection schemes must account for bidirectional power flows. Anti-islanding protection ensures that distributed generators disconnect when needed to avoid operating in isolation unintentionally. Protection settings and communication schemes are adapted to maintain selectivity in networks with increasing amounts of distributed generation. Maintenance and testing maintain the reliability of protection systems. Protective relays are tested for correct settings and response. Circuit breakers undergo timing tests and condition assessments. Communication links used for pilot protection and for PMU data are verified. Protective coordination studies are updated when system changes occur, such as new lines, new generation, or changes in operating patterns. In summary, protection systems detect abnormal electrical conditions, make decisions based on predefined criteria, and operate switching devices to isolate faults. They employ multiple techniques, including overcurrent detection, differential comparison, distance measurement, pilot protection, and synchronized measurements. Coordination, redundancy, and testing ensure that faults are contained to limited sections of the grid and that normal operation can continue elsewhere. These processes occur continuously and automatically, allowing large electrical networks to respond to faults with minimal manual intervention. Long-term operation of an electrical grid is a continuous process of coordination, monitoring, and renewal. Systems that must run for years and decades are organized around cycles of work. Those cycles include daily balancing, seasonal adjustments, scheduled maintenance, equipment lifecycle replacement, and long-range planning. Each cycle has its own timescale and its own methods. Together, they form a system that remains operational over extended periods. Real-time control systems handle immediate balancing tasks. These systems keep frequency and voltage within acceptable ranges every second. Automated controls respond to small variations in generation and load. Operators monitor these systems in control centers. Remote telemetry provides continuous data about flows, voltages, and component status. This constant stream of information supports short-term decisions and triggers automatic responses when needed. On a timescale of minutes to hours, dispatch coordination manages generation schedules and reserve allocation. Reserve capacity is held ready to respond to unexpected changes. Some reserves act almost instantly through automatic controls. Others can be brought online within minutes through dispatch commands. Scheduling takes into account expected demand, forecasted weather, and the operational status of major assets. These decisions are updated regularly throughout the day. Maintenance planning operates on a weekly to monthly rhythm. Routine inspections are scheduled to align with lower demand periods when feasible. Planned outages for equipment replacement or major testing are coordinated across regions to avoid concentrated impacts. Work orders are prepared in advance. Teams follow established procedures for isolation, testing, and restoration. Coordination involves operators, field crews, planners, and contractors. Documentation tracks each task and its completion. Long-term reliability depends on lifecycle management of assets. Major components have different lifespans. Transformers, for example, often remain in service for several decades under normal conditions. circuit breakers and protection relays have planned intervals for testing and calibration. Cable systems and overhead lines receive periodic inspection and maintenance. Asset managers maintain inventories and replacement schedules. They consider degradation mechanisms such as thermal stress, corrosion, and mechanical wear. Decisions about replacement versus repair are based on condition data and economic planning. Condition monitoring and predictive maintenance have become central to long-term reliability. Sensors measure temperature, vibration, oil quality, and electrical characteristics. Data is collected continuously or at regular intervals. Analytics identify trends that indicate deterioration. Predictive models estimate remaining useful life for individual components. Maintenance can then be scheduled before failure occurs. This reduces unplanned outages and concentrates work when it is least disruptive. Inspection techniques have diversified. Visual inspections remain common for accessible equipment. Infrared imaging detects hotspots in electrical connections. Dissolved gas analysis helps assess transformer insulation health. Drones and aerial platforms inspect lines and towers in remote or difficult terrain. Some inspections use remote cameras and robotic devices for confined spaces. Each technique contributes specific information about the condition of equipment. Coordination extends across organizational boundaries. Transmission operators, distribution utilities, generation companies, and regulators share planning information. Interconnection agreements define responsibilities for facility operation and maintenance. Regional organizations facilitate bulk system planning and outage coordination. During planned maintenance, operators share schedules to avoid simultaneous outages on critical corridors. This regional view reduces the likelihood of capacity shortfalls. Long lead times influence planning for major components. Transformers, large turbines, and certain specialty parts can take months or more to procure. Procurement planning anticipates these timelines. Stocking strategies balance the cost of inventory against the risk of extended downtime. Contracts often include terms for expedited delivery and mutual assistance arrangements. These arrangements allow utilities to share resources in response to larger system needs. Workforce development is part of long-term operation. Technical skills are required for routine and complex tasks. Training programs include classroom instruction, simulation exercises, and on-the-job mentoring. Certification and licensing ensure that personnel meet regulatory and industry standards. Succession planning addresses retirement and skill transfer for experienced staff. Clear procedures and documentation support consistent execution of maintenance tasks. Testing and verification are recurring activities. Protective relays are tested at intervals to ensure correct operation. Circuit breakers undergo mechanical and electrical testing. Emergency generators and black start units are exercised periodically. These tests confirm readiness and reveal maintenance needs. Test results are recorded and reviewed as part of the asset management process. Operational planning covers a horizon of months to years. Capacity, expansion, transmission upgrades, and generation retirements are evaluated in multi-year plans. These plans consider demand projections, technology changes, and regulatory requirements. They inform investment decisions and rate proceedings. Public and stakeholder consultations are part of the planning process in many jurisdictions. Regulatory frameworks influence long-term practices. Reliability standards, Reporting requirements and environmental regulations set constraints and expectations. Compliance programs track adherence to these standards. Audits and oversight occur at intervals defined by regulators. Policies shape incentive structures for investment and maintenance. They also influence how costs are allocated and recovered. Information technology supports long-term stability in several ways. Supervisory control and data acquisition systems provide monitoring and remote control. Energy management systems perform dispatch optimization and contingency analysis. Cybersecurity measures protect control systems from unauthorized access. Redundant communication paths and backup systems reduce the risk of single points of failure. Regular software updates, patch management, and security assessments are part of operational routines. Risk management practices are integrated into maintenance and planning. Probabilistic assessments estimate the likelihood and impact of equipment failures. Scenarios consider extreme weather, load growth, and component aging. Resource allocation reflects these risk assessments. Contingency plans specify steps for restoring service after significant disruptions. Exercises and drills test coordination and recovery procedures. Mutual assistance and contingency support are institutionalized in many regions. Agreements allow utilities to request personnel, equipment, and materials from neighboring organizations when local resources are insufficient. These arrangements are activated according to predefined protocols. Shared resources help manage the consequences of widespread events and speed restoration efforts. Capital planning and budgeting occur on long cycles. Utilities prepare multi-year capital plans that prioritize projects based on condition, capacity needs, and regulatory requirements. Funding mechanisms vary by jurisdiction. Investment decisions are weighed against operational needs and projected demand. Depreciation schedules and asset valuation inform the financial treatment of infrastructure. Over decades, gradual change influences operation and maintenance. New technologies alter monitoring capabilities and control strategies. Workforce demographics shift. Regulatory environments evolve. Practices adapt through incremental changes. Documentation and institutional knowledge help maintain continuity through these changes. Continuous operation over long periods relies on the interplay of routine tasks and strategic planning. Real-time controls, scheduled work, condition-based maintenance, and long-term investments all contribute. Coordination across organizations and across timescales maintains the system's functioning. The processes are methodical and repeated. They form a framework that supports sustained operation of electrical grids across large regions.